Hello, and welcome to Tomversations, a regular technology conversation with me, your host, Tom Hollingsworth, about a variety of enterprise IT topics. Today, I'd like to dive a little bit deeper into security. Specifically, I'd like to talk about cryptography. One of my favorite movies of all time is Sneakers, a 1992 film by Phil Alden Robinson, starring Robert Redford, Dan Aykroyd, and Sidney Poitier. It's a somewhat of a spy thriller, with the MacGuffin being a mathematical computer capable of breaking encryption. It was developed by a mathematician, subsequently stolen, and spends most of the movie being stolen back and forth by our heroes and the villains. In 1992, the idea of creating some kind of a computer that was capable of breaking all known forms of secret communications was somewhat of science fiction. Today, thanks to the advent of an algorithm and the race to create a supercomputer, we are closer than we've been in quite a while to creating a quantum computer capable of breaking encryption. Before we get into that, let's take a real quick side note to understand how public key encryption works. It's all based on work done by Ron Rivest, Adi Shamir, and Leonard Adleman, collectively known as RSA. These three developed the algorithms for encryption that would later form the foundation for public key encryption. In short, RSA uses two large prime numbers to create a third number. That third number serves as a public key that is used to sign messages and verify identity. The private key can only be determined if you know the two prime numbers that were multiplied together to form the public key. As long as you keep those two prime numbers safe, your private key is safe. RSA is built on the idea that modern computers are incapable of factorizing that number in a time frame that's reasonable. For example, for a system that uses 128-bit encryption, there are 2 to the 128th power possible solutions to that problem. That's a lot of potential solutions, and a computer working as fast as possible still won't be able to determine all of those. Now, in 1994, just 2 years after Sneakers came out in theaters, a man named Peter Shor developed an algorithm that said if there was a way to find the factors of a number quicker, or determine a way to shortcut through that factorization process, even a modern classical computer would be able to quickly factor keys. Peter Shor's work was canonized in something called Shor's algorithm, and it kickstarted the race to create something called a quantum computer. Quantum computers work a little bit differently than classical computers, and a complete discussion of what a quantum computer is capable of doing and how it does it is beyond the scope of this particular video. But suffice it to say, they're very, very powerful because they don't think in simple terms of 1 and 0 anymore. One of the things they excel at is the ability to factorize large numbers very quickly. Shor's algorithm, when properly implemented, will allow any classical computer teamed with a quantum computer of sufficient power to rapidly disassemble encryption keys by rapidly factoring down into component parts. So Peter Shor created an algorithm that's capable of completely defeating encryption. In the intervening 25 years, companies like IBM and Google have been racing to create a super powerful quantum computer. You may have heard news stories last year that Google had achieved something called quantum supremacy. What is that? Quantum supremacy is when a quantum computer is capable of solving a problem that a traditional classic supercomputer is either unable to solve or can't solve in a reasonable amount of time. All right, so that means that a quantum computer can now break all classical encryption. That's not entirely accurate. Quantum computers are extremely fast, but one of the other problems they come into is precision. Remember I told you that quantum computers don't think in ones and zeros? Well, that's a huge benefit for them to be able to do things like rapid factorization. It's also a huge detriment because think about something like a light switch in your room. It's either on or it's off, right? But what if there's a short in the system? Sometimes it might be on, sometimes it could be off, and the state of the switch may not match the state of the light in your room. So there are multiple different situations that apply rather than simple on and off. This is a problem that plagues quantum computers today. They may be super fast, but they're also noisy. Quantum noise interferes with the precision of a quantum computer. And because of the way quantum computers performed calculations, any amount of noise without error correction can lead to incorrect results. And when you're trying to factor extremely large numbers like those that are used in 256 or 512-bit encryption schemes, even the least amount of imprecision in your calculations can lead to wildly different and incorrect results. Quantum computers need quantum error correction because of the way that qubits operate. Qubits are the computational units of a quantum computer. The more qubits, the more powerful it is. However, the more qubits it has, the more likely it is to develop noise. Shor's algorithm for very simple numbers only needs 2 qubits. However, most reasonable calculations about the size of a quantum computer necessary to break even the simplest form of encryption range from 48 qubits on up. And each of those qubits, even though theoretically is capable of doing a lot of things, inherently in practice are very unstable and very prone to noise. Think of it like a sports car with a very large engine and no steering wheel. We can go in one direction really fast. We just can't determine what direction that is. Okay, so we have a quantum computer that's super powerful and capable of breaking encryption when it's able to get all of its quantum noise problems under control. Realistically, it's 3 to 5 years before the quantum computers are powerful enough to take on large encryption algorithms. Before they can clarify the noise problem, more like 5 to 7 years. So we're safe, right? Robert Redford and Dan Aykroyd don't have to worry about anybody stealing their data anytime soon. Well, like all good technologists, we didn't just sit around and rest on our laurels while we hoped that someone was going to eventually find a way to get past this problem. Since 2016, there has been a large-scale effort to develop a post-quantum cryptographic algorithm. Why is this important? Well, remember we talked about RSA being the foundational part of a lot of encryption technologies that we use today? Things like OpenSSL, TLS, and SSH are all using a form of RSA encryption. If a quantum computer with sufficient precision and power is developed in a reasonable amount of time, all SSL and TLS encrypted traffic across the internet could very well find itself able to be broken very quickly. Thanks to the efforts of companies like Microsoft, Ericsson, and DigiCert, there has been a significant amount of research that's been done to create a post-quantum cryptographic algorithm. Creating a post-quantum cryptographic algorithm isn't as easy as it sounds, because one of the things that makes it quantum-proof is to create extremely large key sizes that are unable to be factored quickly, or can defeat a low qubit quantum computer. Any sufficiently large algorithm that's capable of defeating a quantum computer will also overwhelm a classical computer, because the need to transmit large keys as well as being able to decrypt information quickly is a trade-off that must be taken into an account. And we're talking about what one would consider to be a classical computer, such as a laptop or a mobile device. Think about the processors that are being used in things like IoT. We still want to be able to secure that data. We don't want it flying anywhere unencrypted. But the processors in most IoT devices are significantly less powerful. And so feeding them a post-quantum cryptographic algorithm with a sufficiently large key will likely cause them to fall apart. This is why there has been a significant amount of research going into this. The US government's National Institute for Standards and Technology, also known as NIST, has been carefully evaluating the proposed cryptographic algorithms for standardization. When they started, they had 69 algorithms that they had to sort through. As of July 2020, in the third round, 3 finalists have been selected for possible standardization: Crystal's dilithium, Falcon, and Rainbow. There are an additional 8 finalists, which are essentially backups. They're unlikely to be selected for standardization by the end of the 3rd round, but could potentially be selected in the future. The future of quantum cryptography and post-quantum cryptography is essentially a race against time. As we often say in artificial intelligence, the second after an artificial intelligence algorithm becomes self-aware, the genie's out of the bottle. Now, when we say self-aware artificial intelligence algorithms, we're really talking more in the realm of science fiction, but realistically speaking, we're a lot closer to science fact today than we were in the 1950s and 60s. Likewise, when Peter Shor developed his algorithm in 1994, the idea of creating a computer capable of breaking encryption was a far-off fantasy at best, and we're a lot closer than we were. It's a race against time to develop a quantum-proof encryption algorithm and implement it in modern technology and protocols such as TLS and SSH before a quantum computer asserts enough supremacy and precision to be able to decrypt those communications. It's always the race against the secrets and the secret breakers. Thank you very much for tuning into this episode of Tomversations. I hope you found it enlightening. Show notes will include some articles to read up on quantum computers, quantum cryptography, and some other fun things. You can always find the most current episode of Tomversations on our website at gestaltit.com. I recommend you visit there to check out some other interesting things like our Gestalt IT Rundown weekly news show, our Gestalt IT Checksum conversation series, as well as our on-premise IT Roundtable podcast. I hope that you'll tune in for the next episode of Tomversations, where we'll tackle another interesting technical topic, and I look forward to seeing you all in the future.